problem that's disproportionately affecting certain areas, and the Mid-Atlantic region is one of those areas, specifically the Delmarva and the Chesapeake Bay. That is sea level rise and saltwater intrusion in these coastal agricultural areas. So this talk has sort of three sections. I'm going to go over, just give you guys a general background information on climate change globally and regionally, as well as saltwater intrusion, what that term actually means and how those two things are linked. And then my particular research project, where I am looking at this phenomenon in Somerset County, so in the lower Delmarva. And some of the things I found so far, this is my second summer looking at this in this area. And then some of our ideas for really how to address this problem, whether it's through alternate cropping systems with salt-tolerant crops, or if land does ultimately have to be abandoned, what are some conservation strategies that we can use to help farmers as this land transitions with these environmental changes. So just to give you an overview of climate change, I'm sure a lot of you have seen a lot of the information I'm going to show you before, but just to kind of refresh everyone's memory and to show you how everything ties into each other, both on the global scale and the regional scale. And then this background picture here was actually taken in the lower Delmarva, and this was not during a storm. This is actually just during a high tide. This is, yeah, exactly. So this was, you know where it is. So it spilled onto the road. The Chesapeake Bay is actually a foot deeper than it was at the start of the 20th century, meaning that these storm surges will come higher and higher onto land. And in the Chesapeake by 2100, if current trends continue, the bay is actually, the sea level is expected to rise by anywhere from 3 to 4 feet. That's kind of a modest projection. Some of the more extreme worst case scenario projections are looking at almost 6 feet. So you can think in an area where a lot of the land is only a couple feet above sea level to begin with, that has huge implications. So just to show you global temperature trends, this is from the IPCC's latest report. So the IPCC is the International Panel on Climate Change, which is a collaboration between the world's leading climate experts. And what this graph shows is, this is from the year 1800 to present day, and at the top you can see these are annual averages of temperature. Blue is ocean, the orange is land, and then the black here is the average. So you can see that the ocean and the land coincide pretty well. And then in both the annual averages and when you take these decadal averages, you can see that since about 1990, these temperatures have really been dramatically, basically exponentially increasing. And what that is translated to is about a 1.1 degree Fahrenheit increase since 1990. So this is globally. So let's talk about these projections on a regional level. So this is a map from the U.S. Global Change Research Program. They actually just released parts of their latest report on climate change. You can go find this on their website. And these are projected increases in the number of days over 90 degrees Fahrenheit. This is in the Mid-Atlantic northeastern region. So at the top here you have our historical climate, and then under these two different scenarios, so one's a low greenhouse gas emission scenario and one's a high scenario. The thing to pay attention to is in both cases, whether we have low or high emissions, we're going to see a lot more of these days over 90 degrees, particularly in the Mid-Atlantic. So, and just to show you a few more trends of what's going to happen in sort of the Chesapeake Mid-Atlantic region. And these are not projections, these are what we've already measured. So we see these numbers of frost days going down, we see total precipitation increasing, and then we see the growing season length increase as well. And of course you look at these and you think maybe there are some benefits to having longer growing seasons. more precipitation, less frost, but there's also a lot of negative consequences too, like need for more irrigation because of hotter days, more pest problems, flooding with heavy precipitation. And we're seeing too with a lot of these precipitation events that they're becoming more extreme events or dropping more precipitation per event. So I talked about temperature, and I want to tie that to sea level rise and these sea level rise trends and how they're sort of matching up, correlating with these temperature trends. This was taken from that US Global Change Report as well. And these are sea level trends reconstructed from about 2,500 years ago to present day. So we didn't have thermometer temperature measurements till about the 1800s, but a lot of this was reconstructed from other proxies using ice cores and sediments and that kind of thing. But even if you focus on just the temperature, direct temperature measurements since the 1800s, you still see this dramatic increase in sea level, particularly in the Chesapeake. The sea level, I talked about this before, rose about a foot during the 20th century, which is about twice as fast as it had in the previous several thousand years. And if you look at these lines here, so these are projections for how the sea level is expected to increase by the end of the century under different scenarios. So at the one end, you have a very low emission scenario, and then the red, you have a very high emission scenario. So we're not sure which one it's going to be, but we can see that in every case, the general trend is an increase. So over the period from 1901 to 2010, the global mean sea level rose about 20 centimeters, which is about 8 inches. And in the Chesapeake, the forecast is for a 2-foot rise by the year 2050. So let's talk about nuisance flooding and how this ties into sea level rise and what exactly that means. So nuisance floods are also called sunny day floods, and there are these tidal floods not caused by storms, so like the one I showed you with the picture of the water spilling over the bridge, and they happen just from tides, and they've increased about 5 to 10-fold since the 1960s in several US coastal cities. And this report measured 25 different Atlantic and Gulf Coast cities and saw this same trend over every single one. So these rates of increase are actually accelerating. So in this graph here, you have the top Charleston, South Carolina. All the orange bars are actual measurements, and then these are projections here. The lower projection is based on current trends and current emissions, and then these are some more extreme projections. And you can see even with sort of the lower estimate, Charleston, South Carolina is expected to see 150 nuisance flood days per year, and then you see a similar trend on the West Coast in San Francisco. So interesting to have that agreement almost everywhere in the country. And I'll show you what that actually looks like on my field. So these are my fields in Somerset County, Maryland. And these are the results of some of those nuisance floods. So on the left here, this is a soy field, and you can actually see there's algal growth on the field. So this is a saltwater algae that's taken over part of this field, and these crops have all died off here. And then on the right-hand side, this is saline water on the field. There's a ditch in the background nearby, and we measured salinity. This is on a cornfield, and it was about 5 parts per thousand. So again, from that nuisance flooding. Just to show you some more examples of how climate is changing in the mid-Atlantic. This was Annapolis during Hurricane Isabel in 2003. So I know everyone's been hearing a lot about hurricanes in the news recently with Hurricane Irma in Florida and the Caribbean, and then of course Hurricane Harvey in Houston. So these hurricanes are expected to become more frequent and more intense. So in addition to the nuisance flood, we're at greater risk for these huge storm surges. This is Tangier Island, Virginia. So it's not too far from here. It's off the west coast of the Delmarva in the Chesapeake Bay. And since 1850, the island's landmass has actually been reduced by 67%. Some of this is due to soil erosion, some of this is due to sea level rise. And under that mid-range sea level rise scenario, much of the remaining landmass is expected to be lost in the next 50 years, and the town will have to be completely abandoned. So you can actually still take ferry rides out to that town now, but as you can see from this picture, it's extremely vulnerable area. This is Holland Island, Maryland. Some of you may have seen this picture before. It's become pretty famous. So this is an island that was once 5 miles long and home to a fishing community of about 360 people. There was more than 60 homes on the island, but this combination of erosion and sea level rise forced everyone to leave, and it's been slowly receding into the Chesapeake. This was last year. This house fell into the bay last year, and the island has completely disappeared. So these are just two examples of a lot of islands in the bay that are experiencing this. And this was Crisfield, so this was during Hurricane Sandy, from which this area is still recovering and may not fully bounce back from. This was downtown Crisfield, and a 3-foot rise in sea level would permanently submerge much of Crisfield. And this is actually where some of my farm sites are located. So in Maryland, about 24,000 people, about 17,000 homes, and about 160,000 acres are within this 3 feet of the bay's current sea level. So an extremely vulnerable area. And one more picture. So this is Ocean City, actually, also during Hurricane Sandy. So this was a storm surge that came up onto the boardwalk. So I've showed you all these pictures of sea level rise and sort of given you background of these temperature changes. So why exactly is the sea level rising? So it's the thermal expansion of the oceans. As the oceans are warming, they're expanding and their volume's becoming greater. Then it's partially from just the melting polar ice caps are also contributing to the greater overall volume of our oceans. And then we have this particular phenomenon in the Chesapeake, and this occurs in some other areas of the world, where we're experiencing glacial rebound from the last ice age. And so I'll explain that a little bit better. So during the last ice age, the maximum extent of the ice sheet ran through part of the Delmarva Peninsula and caused the land to actually bulge up kind of like a seesaw. So the land under the ice was depressed, and the land that was not under the ice was pushed up. When that ice sheet receded, the seesaw started to go in the other direction. So ever since, the land, for the past few thousand years, the land has been sinking back down. So you get this combined effect of sea level rise, land subsidence, causing these rates to be double what they are on average globally. And now to connect saltwater intrusion to this concept of sea level rise, I really like this diagram because it gives a really good schematic of what's kind of occurring underground in a lot of these coastal areas. So you have this zone of freshwater, these freshwater aquifers, and then you have this area where this mixing zone where they meet saltwater from the bay or tidal creeks or the ocean. And the freshwater, because it's less dense, sits on top of the saltwater, and this boundary is not set, so it shifts depending if there's more freshwater input, especially in the Chesapeake, or if there's a hurricane that maybe pushes that saltwater front up farther into the bay. So this boundary is constantly shifting. If there's a drought, that can also cause saltwater incursion, and then just keep in mind that things like droughts are projected to become more intense and more common when they do occur due to climate change. So just some thoughts on how this boundary will change with these global changes. And this is what we're seeing essentially seeing underneath a lot of our farm fields. So just to talk about the problem of salt in general, this is a map from USDA, and this is just total land in the U.S. that's impacted by salt right now. So some of this is due to saltwater intrusion. A lot of it is out west, but you can also see there's this zone here that's pretty heavily affected in the mid-Atlantic. So 6% of land globally is impacted by salt, and that includes 42 million acres of irrigated land in the U.S. So salt is a huge problem. And then just to zoom in on the mid-Atlantic region, and you can see how much of the Delmarva is affected by that, and of course much of that is due to saltwater intrusion. Again, just to kind of blast you guys with pictures from my field. So this was a picture taken on one of our fields, and this is saline water. It's about 4 parts per thousand, which is much higher than these crops can tolerate. So now that I've given you guys kind of an overview and some background information on the problem, I want to go into my particular research and what I've been looking at on these fields. So this is a picture of a lysimeter, and it's a basically soil solution access tube. So I put them into the ground, and you apply, has a ceramic tip, and you apply vacuum pressure to it, and you come back the next day and you collect the soil pore water, and then you can take that soil pore water and measure things like salinity and nutrient levels on it. And then on the right here we have a soil core that we took, and you can see that some evidence of water logging in these soils at relatively shallow depths. So kind of the other component of this research, so in addition to saltwater intrusion, we have the issue of legacy nutrients in these fields, particularly phosphorus, and a lot of that is due to the intensification of poultry farming in the area. So right now, and this is from the Chesapeake Bay program, they estimate about a quarter of agricultural phosphorus inputs in the bay are due to poultry farming. So you have this like current contribution of nutrients. And then, as I'm sure if you went to some of the talks yesterday, you heard about this concept of this legacy phosphorus. So these nutrients that have been locked in the soil from decades of fertilizer application. And I'll show you guys in a minute here, there's implications for as the soil chemistry changes due to saltwater intrusion, it can actually unlock these nutrients from the soil and push them out into nearby tributaries. So these are more pictures I've taken on my sites. On the left here we have a field where salt water actually came up through the groundwater table, and it was a really hot day, so it, through capillary action, pulled the salt water up, and the salts deposited, precipitated out on the upper soil layers, forming sort of this crust here. So it looks like a salt flat. Doesn't really look like anything you'd find in Maryland, but it is. And the right here, so this was the pine forest adjacent to these fields. And you can see the snag of dead trees here, and that's where the salt front has been moving in over the years, so these trees can only tolerate a few parts per thousand salinity. We went and took a soil solution there and measured it, and it was about 5 parts per thousand. So if you drive around the Delmarva, you actually see a lot of that. If you go to like Chincoteague and Assateague Islands, it's really dramatic there. You can see where the salt water is intruding by that tree line. So we have this sort of combined problem of saltwater intrusion here, and then legacy nutrients and like how they interact. And so I'm going to show you some data that sort of explains that a little bit better. These are what a lot of our fields look like in these transitional areas where they're meeting these marshes. The marshes are actually migrating inland. They're migrating up onto these fields. So on the left here you have a salt marsh plant, Spartina patens, and then here's the cornfield. So you can see the transitional area where they intersect, and then these bare areas on the field are actually those places where the salt has hyperaccumulated. Maybe those areas were slightly lower elevation, and nothing will grow because it's actually hypersaline there. So we've gone and taken measurements of some of these bare areas, and they've been up to 35 parts per thousand, which is basically the salinity of ocean water. So obviously there's a huge difference in the soil chemistry of an agricultural soil and a marsh soil. Marsh soils are waterlogged at least part of the time. So you go from these oxygenated conditions to these very low oxygen conditions, different plant communities, and then there's, because of the low oxygen, there's interactions in the soil that can cause nutrients to be unlocked and released. So I talked about global and regional sea level rise predictions. I want to talk particularly about the county that I work in because it's very susceptible, and show you guys some projections under different sea level rise scenarios. So on the left here we have the North American coastal plain in green, and then the pink is the area of landmass that is expected to convert into open water under 3 feet of sea level rise. And then if you zoom in here on Somerset County, so the red here is open water, the white is the county boundary, and you can see under 1 foot of sea level rise, and then under 3 feet, which is a modest projection for the end of the century, that a lot of the county will actually disappear and be converted to either open water or tidal marsh. Once again, so this is another salt damaged field, and then here's some of our data on these kinds of areas. So, these measurements are at a deep and a shallow depth in the soil profile, so 25 centimeters into the soil profile and then 50 centimeters in these areas, in these sort of transitional zones. So we took these measurements in 6 different fields in Somerset County, and these were our averages. So you can see at the high end, we're measuring salinities as high as 10 parts per thousand in these areas. In the low end, 2.5 parts per thousand, which is still higher than corn can tolerate. And then so just to show you what these sites look like in satellite imagery, so you can get a sense of really how vulnerable they are along the west coast of the Delmarva Peninsula in the Chesapeake Bay. And the average elevation here is about 2 feet. So even a small few inches change in sea level can really, that's a large percentage of the elevation of these areas, so it can really dramatically affect them. And then just to zoom in on one of our fields, so this field is bordering a tidal creek here, a brackish tidal creek. And you can see, even through satellite imagery, the evidence of salt damage on the field. So actually all these sort of brownish grayed areas of the field are spots that have been affected by saltwater intrusion. And the field's pretty close to this creek. We went in and we took point salinity measurements, and you can see they range anywhere from almost fresh water in certain spots to brackish water. So you can see like there's extreme variation and variability across just a small area that makes it difficult to predict what areas are going to be most affected by saltwater intrusion, and how much nutrients are going to be unlocked from the soils. So this is a map of the mean surface salinity of the Chesapeake. This was averaged over, this was from 1985 to 2006, taken in the springtime. So you can see these sites, I circled Somerset County here, fall in this mesohaline range where the salinities are anywhere from 5 to 18 parts per thousand. Just to give you a sense of what like the lower threshold of these areas are and how they may increase over time. And again, for reference, to show you the picture or show you the graph of the salinity measurements we took on our fields. So I like this aerial view. This was a farm in the lower Delmarva because it really illustrates sort of the different ecosystems that you see around these farms and these different transitional zones between them. So we start off on our field here, and then that field becomes flooded at its edges and drains into these tidal creeks and these marshes. And usually we have adjacent forests which also become flooded, drain into these marshes as well. So I just want you to keep these ecotones in mind as I show you some data from these sites. So we went out to all 6 sites and we sort of found these ecotones on each site, and we took nutrient salinity measurements at each one. So in addition to the ecosystem transitions, we have these transitions on our field. I talked about them a little bit, but I'm just going to lay out specifically the points along the field where our transect, where we took our measurements. So we have, and this is a satellite image of one of our fields that's particularly damaged by saltwater intrusion. So we have what we call sort of the center of the field where the crops are growing pretty well, out onto these edges where they're not doing so well, and then that bare patch I sort of showed you guys before where we get these hypersaline conditions leading to these edges of these ditches where we see a lot of marsh plants growing, and then finally out into the open marsh surrounding the fields. And this is an extension of the graph I showed you earlier. So I already showed you the average measurements on the field themselves, on that field edge where the plants start to not do so well. In the bare areas where we see those even higher salinities, those hypersaline conditions, and then in these ditches are essentially brackish water. So I put on here for reference the threshold for what corn crops can tolerate. These are in parts per thousand here. And then the threshold for what wheat and soy can tolerate, slightly more salt tolerant, but still both fall well below some of what we're actually measuring on these fields. So now to bring the nutrient piece of this back into the equation, so with these soil solutions, we also measured phosphate, so soluble phosphate, across these different ecotones. And you can see that phosphate levels are extremely high, really in every ecotone, but most of it is going into these marshes. So this is the threshold for eutrophication right here. And it's pretty high in the fields with a lot of variation. This is depending on the individual farmer and their farming practices. And then you see this overwhelming trend that everything's ending up in the marsh. So this is confusing to some because a lot of people are told that, well, marshes are nutrient buffers. This can be true to some extent, more so for nitrogen, but what we're actually seeing for phosphorus is that because of these changes in soil chemistry, and I'll talk a little bit about the composition of seawater and why that is, we're actually seeing this net flux of phosphate into these marshes, and that's going into these tributaries. We looked at ammonium as well, and we see the same trend actually, where it ends up in these marshes. We don't see nitrate really in the marshes because of denitrification, but we still see significant amounts of ammonium as well, though phosphorus is more the focus. So why is saltwater doing this? So it's a complex mixture of ions, and it's specifically interactions with the soil and the sulfate component of seawater. In addition, you have more sulfate coming from gypsum, so a lot of people are applying gypsum to these fields to try to reclaim these sodic soils, but that can actually potentially be contributing more to the problem in these particular areas. So essentially, phosphorus is bound up in aluminum and iron oxides, and under low oxygen conditions, so when these fields become waterlogged, they can actually release the phosphate, and the sulfate will preferentially bind to those metals, causing them to precipitate out in the soil, and the phosphate is then free to travel through the water column. And just to show, we actually took measurements of sulfate, and you can see that sulfate is increasing as we go from the center of the field towards the marshes. So it's moving in onto these fields. So this is a Malick P test we did. So we actually, in addition to looking at soil solution, we also did extractions on these soils. And this was along that transition on the field. So you see, so this is soil depth right here. We cored down to 120 centimeters and converted these to fertility index values. So anything over 100 is an excessive amount of phosphorus. And we're seeing, in some parts of these fields, we're seeing levels reach 350 to 400. And we see it moving out onto the edge of the field. Then we measured the soluble phosphorus in the ditch bordering this particular field. This was a cornfield, and we measured 0.8 milligrams phosphorus per liter. So now that I've bombarded you with the kind of complexity of this problem, I want to talk about some potential solutions and what we've been thinking about so far. So this is really our second summer looking at these sites, and we're installing a lot of long-term monitoring equipment like constant salinity loggers, and we're going to actually keep looking at these areas, hopefully 10 years plus into the future. And we just started this summer some saltwater, salt-tolerant crop trials. So we're testing out different crops that we might be able to grow on these marginal areas. So just a little overview of what those plots look like and sort of our setup for that. We're still growing, so we haven't gotten the results back yet, so hopefully I'll have those data next summer. This is one of our fields. You can see clearly the salt damage on the map, and this is what our setup looks like. And then just to break that down further, we have these rows with little 1 meter buffers between them. And the crops that we're growing in particular, so the salt-tolerant crops that we're trying out are barley and switchgrass. And our controls are we have a bare area. We're allowing some plots, we're allowing weeds to grow in. And then, of course, we're going to try soy sort of as a control, knowing that probably won't do well in these soils. So I'm curious to see what comes of this. So that's one aspect, is sort of managing, trying to manage as things change. But eventually, these areas are going to become so salinized that we won't be able to grow much at all. So then the question becomes, how can we put this land into conservation? How can we help farmers put this land into conservation easements? So I'm sure a lot of you have heard of the CREP program. So it's a state and federal partnership where farmers are paid an annual rent to take their land out of production. And then native plant communities are actively established. So I have some data so far on enrollment in the CREP program in Maryland, Virginia, and Delaware. So these are data from a site called Environmental Working Group. You can actually go on there and look at any kind of farm subsidy payment you want. And in Maryland right now, there's about 2,600 acres in the CREP program enrolled in the wetland restoration. In Delaware, it's about 346 acres. And then in Virginia, it's only about 220 right now. And I have some graphs showing what those conservation reserve program payments are year by year. So you can see that quite a bit of funding is allocated to these programs. And in Maryland, it was actually the third highest farm subsidy payment program. So this is just to give you an idea of the numbers, this is how much has been allocated to it from 1995 to 2014. We also have this other program called the Wetlands Reserve Program, and this is also a way to take land out of production and put it into a wetland conservation program. So we may see a trend towards more and more land being put into these conservation easements for wetlands as this problem gets worse in these coastal areas. And then again, just to show you, these are the numbers for Delaware. And these are the numbers for Virginia. So just to kind of recap, what are our goals in doing this research, and like what do we hope to get out of this project? So we want to get a better understanding of how nutrient cycling is occurring with saltwater intrusion. It's a much different system than what we're used to looking at in these freshwater systems. How can we plan strategically for what's going to happen to this land, what's going to happen to these areas? How can we help people to enroll these marginal lands in these programs so they can still get the most out of them? And then, is there a potential to attract stakeholders to these areas? So just real quick, if you are curious about any of the data presented or any of the resources I drew from, I have links here to some of those things. So the IPCC reports on climate change and the US Global Climate Change Report as well. And then the USDA released this report on adaptation resources for agriculture, specifically in the Northeast and in the Midwest. Thank you.
Questions?
Just one quick question for you. Have you done any literature review or search of what they've done in the Netherlands? Basically, a lot of work's been done in the Netherlands over the last centuries to reclaim land from the sea and the cropping systems that they've established on that land. So, I mean, there's probably either through Wagenheim or one of the research stations in the Netherlands, you probably can get some information that may be applicable.
You're the second or third person to mention that to me, so I will definitely.
I've spent time there. I've spent time at the thing, and it's interesting what they've done. And they had back in the 50s, one of the North Sea storms came in there and over swam their dikes and whatnot. And they basically went back in and reclaimed a lot of that land, growing salt marsh hay, and then and there was just there's some real, you know, it might be old, but there's some stuff that's been historically done there to reclaim and salvage some of this stuff that it'd be well worth your effort if you're working on a PhD to go and review some of that literature and see if some of the crops and what they've done may be applicable to the Eastern Shore.
Thank you.
Salt marsh hay is definitely an option.
Yeah,
Yes, it is.
absolutely.
I mean, it's amazing.
Anybody else? Go ahead.
Can you talk about the kind of the tolerance of various crops that you're looking for? Are we, as I understand it, once areas become salted, you're basically trying to push that salt back out of the soil. That's the remediation. You're not having these crops actually uptake any of the salt and actually remove it in any way, right? It's more of a push.
Right.
Back down into the
And so in this case is interesting too, because unlike a lot of systems or fields where they're trying to do that, we have this problem of this very shallow and rising groundwater table. So there is no leaching the salts out of these soils, and there's no, even if the plants uptake a lot of the salt, it's just going to keep coming in. Oh, I'm actually not sure. Yeah.
Any more? So it's become evident that it's only a matter of time before those areas will not be in ag production. To get to your point, yeah, in California, they pre-irrigate to push salt down enough in the profile so that they can then grow their corn crop and the like. And yeah, when I saw that, I was like, I can't believe that. But you got to do what you got to do, right? All right, Danny, thank you so much.